All right, so before we start, look up here. And let's look at a nice curve. All right, so this thing's fun. The goal throughout Chapter 3 is to find special points. There are lots of different kinds of special points. What we're going to look at today and probably Monday is extrema, which is a general term for maxes and mins. So when we talk about find the extrema, we're talking about find the maxes and find the mins. And for something to be a maximum or a minimum, it doesn't have to be the very highest point or the very lowest point. Please shut out the noise of the crazies. It's probably shouldn't call them that while I'm being recorded, but whatever. They should be in class by now. That point is a maximum. It's not the maximum, but it is a maximum because it's higher than all the surrounding regions. So we would call that a relative or a local max. Same thing here. This is what we would call a relative or a local minimum because it's lower than all the points immediately around it. This point here is the what we call absolute or global maximum because it is the very highest point on the entire curve. So we would call that an absolute max. Then we have another local minimum, another local or relative maximum, and that's it. So those are some special points. All of these other ones I didn't label specifically are relative or local maxes and mins because they're lower or higher than all the surrounding points. And then the very highest point on a curve or on an interval is called the absolute max or min. Any questions with that idea? Yes?
Like a sine and cosine graph, would there be like a max on it?
Yes. So like for a sine and cosine graph, like here, you have a maximum, you have a minimum. This is the absolute maximum, because that's the highest the curve ever gets, and then you'll have that same maximum again over here, and over here, and over here, and over here, and so on. You don't need to find them all.
Also, why you think that part of the sine curve?
Yeah.
Sine graph, what's that called?
An interval. Oh, like that, that's one cycle of the curve. Yeah. Any other questions with that?
The absolute minimum for that graph be negative?
Yeah, which would be, it doesn't really have an absolute minimum. Okay. So if the curve heads down to minus infinity on both sides so that there isn't a absolute minimum, we just say there is no absolute minimum. Or we could have like an open circle on the ends, and the same thing would happen. This has no absolute minimum either, because you never reach that point. And you can't establish what the absolute lowest point is because you can always get a little bit closer to this thing. There's like, say it's like, this is -5, then you can say, well, there's -4.9 and -4.99 and -4.999 and so on. You can always just tack on another 0.9, and you're never going to reach -5 because it's an open circle. So this would have no absolute minimum. And that kind of gets us into the extreme value theorem we'll talk about in a little bit. So that's one kind of special points is absolute maximums and minimums. It can be absolute or relative, depending on if you were the very absolute highest or lowest point, or just the highest point in your kind of general vicinity. And that's what we talk about mostly in 3.1, 3.2, and 3.3. You might get to 3.4, but I kind of doubt it. And if we do, then we'll talk about the second type of special point, which is called a point of inflection. And that's a little more nuanced. For a point of inflection, that's going to happen here and probably about there. So these are points of inflection. And that kind of introduces us to a totally new idea. So we have the idea of a curve increasing or decreasing, and that's just, is the curve going up or down. If you're on your phone, you're being rude. Put it away. Come on. So your curve is going up, that's increasing. Your curve is going down, that's decreasing. But there's also like, I don't know, what we call the bendiness of the curve. It's called concavity, and it's how the curve is kind of opening. So the curve is opening down on this first section because it's kind of bending down. So even while you're going up at a slower and slower rate until you're actually going down again. So this is concave down, And then some point along in here, call it right there, the bendiness switches, and now you're bending up, because now this is kind of like a concave up parabola. So this is concave down, and this is concave up. And then we hit this point here, and we're still concave up until about there, and then we're concave down again afterwards. So these points where we switch concavity, where we switch from being concave or bending down to concave or bending up, that's called a point of inflection. If we get far enough, we'll talk about that in 3.4. If we don't get to it, no big deal. We'll cover it next year in AP. So the eventual goal of Chapter 3 is get to the point where we can find all of these fancy special points using calculus and then use them to build a pretty reasonable sketch of the curve without having to rely on a calculator at all. Prince.
Is there always one? Like how where you like label concave down, concave up?
Yeah.
It's just like in that like zone.
Yeah.
Be one.
There's one point. So this is just kind of a rough sketch. So we're kind of like approximating where it is. But there is a single point of inflection somewhere in this region. I'm kind of making a rough guess at it. And there's another one over here. Now, the points of inflection and concavity, that kind of deals more with the second derivative. Maximums and minimums deal entirely with the first derivative. So looking at these maximum points, let's go back to the maximums and the minimums. So at this maximum, what's the derivative of this function? 0, because the curve is flat there. And down at this minimum, what's the derivative? And at this maximum, what's the derivative? That's undefined because it's a sharp turn. And at this point, minimum, what's the derivative? And at this point, what's the derivative? So at all of our maxes and mins, the derivative is 0. So, or it's undefined. So either your derivative is going to be 0 or undefined at your maximums and minimums. And that's going to be kind of what we look at and see with example 1. And then that gets us into this idea of a critical number. A critical number is just an x value that makes your derivative 0 or undefined. And we know that all maxes and mins have to happen there or at the endpoints of the curve if it's closed. Yes?
Are all relative axes of mins going to be a derivative of 0 or undefined?
Yes. So all relative maxes and mins will always happen when the curve has a derivative that's 0 or undefined. An absolute maximum might happen at an endpoint instead if you have a closed interval that has like a definite beginning and a definite end. So that's going to be what we look at today. So that's kind of just like big picture introduction. And what we're now going to do is work on doing this stuff. Questions? All right. So over here, there's the curve that goes with that equation. I would recommend you distribute the 9 and then go ahead and find the derivative of that equation. And once you've done that, plug in 3 for x and see what you get for your derivative. what are you guys doing to get the derivative? Are you dividing it out or using quotient rule? Quotient rule? Okay. Does anybody have an answer for their derivative yet? No?
What the actual derivative is?
Yeah, like what the equation.
I got negative 27 parentheses x squared minus 3 over x to the fourth.
Okay. Could somebody double check and verify what Ryan says is cool? I think he probably reduced it because initially you're going to get an x to the sixth downstairs from low, low, right? So see low, be high, minus high, be low, right? So Ryan, did you distribute that out and then like factor out a common factor before you?
I factored out negative 27 x squared
Okay.
after reducing the top.
Okay, so you multiplied that out, combined like terms, then pulled out a 27x squared and reduced it. Any comments with the derivative or any questions you want to see going into that in more detail? So once we got that, plug in your x coordinate and let's find the derivative at this point. And what are we going to see?
Checker.
Hey, something's wrong.
Yeah, can we go back to that?
Yeah. All right. Ryan, you lied to us.
I just said what I got.
You lied. All right, so let's back up. So if we multiply this out, what do we get here? 18x to the fourth minus, and then 81x squared. Is that a plus or a minus 81? Plus, right? Because we have a minus the negative, so that's going to be a plus.
That's what I
Okay. And then negative 9x to the fourth plus 81x squared. How do you pull out a 27?
can't do simple math.
Okay. So then what can you pull out? An x squared and what else?
9.
9. So take out a negative 9. That leaves you x squared minus 9, right? Over x to the sixth. And then you reduce it and you get negative 9 x squared minus 9 over x to the fourth, right? Because you can cancel out some of these x's. Is that better? No? You still look... Okay. Did you have 9 minus x squared? Okay. So that's a derivative. If we plug in 3, what are we going to get? 0, right? Because 3 squared is 9, 9 minus 9 is 0. So you get 0 over 81, that's 0. And so that's kind of highlighting what I was showing you over there on the picture. This point right here is a, what kind of special point? Max. Is it absolute or relative? Absolute. It is the highest point on that curve, right? So that is an absolute max. But it's also a relative max because it's higher than all the points around it. So the derivative turns out, hey, look, the derivative is 0 at that special point. And that's true for all maxes or mins except for when the derivative is undefined. Okay. I mean, I suppose the curve could potentially do that, but if you go into your calculator and like graph this thing, it doesn't. It keeps going down as you go out to the right and would eventually kind of just travel right along the top of the x-axis. Yeah. But yeah, I mean, you're right. I mean, you don't necessarily know what goes on over here further to the right, so theoretically it could potentially curl and go back up, and then it wouldn't be an absolute max. But it would still be a relative max. All relative maxes and mins, derivative is going to be 0 or undefined. See that? Why did I write b twice? Now, without doing the derivative of absolute value of x, because I don't think I showed that to you guys. Or if I did, it was like one time for like 30 seconds and we moved on. But what's f prime of 0 here? Just looking at the graph.
Undefined.
How do you know it's undefined? Because you got the sharp turn in the curve. So because of the sharp turn in the curve at the vertex, and we're taking the derivative of the vertex because that's where your minimum is, we can just tell graphically, yeah, that derivative's undefined. I think, I might be wrong about this, but I think the derivative equation is x over the absolute value of x. And if that's true, that's the opposite. Do you think it's this? I'm not sure it really makes a difference, but I can buy that. So either way, you plug in 0 and you get 0 over 0 that's undefined, right? So that kind of is the analytical side of things. And then in C, we got our sine curve. And you know the sine curve extends forever in both directions, but we'll just kind of look at this one cycle of it. What's the derivative for sine? Cosine. And we have a maximum at pi over 2 and a minimum at 3 pi over 2. So what is cosine of pi over 2? Now you got to reach back to your unit circle from like February. That's 0. And what's cosine of 3 pi over 2? Yeah. And if you're not sure, you can say, well, he said that the derivative of maximums and minimums should be 0. So go with 0. And you'd be right. So you remember unit circle. On your unit circle, where is pi over 2? At the top. And what's the point up there at the top?
1, 0.
So is it 0, 1, or 1, 0? 0, 1. Because 1, 0 is on the x-axis. Right? So x comma y, there is no x back and forth, so x is 0. It's one space high, so y is 1. Where's 3 pi over 2? On the bottom, and what's that point? Yeah, 0, negative 1. And cosine tells us to look at which coordinate, x or y? X. Right? So cosine says look at x is 0, boom, boom. So again, that's kind of highlighting, hey, look, you have an absolute maximum, you have an absolute minimum at pi over 2 and 3 pi over 2. You plug those into the derivative, at the derivative 0. So that's always true for relative maxes and relative mins. The derivative will be 0 or undefined at those points. And real quick, what do you call it? Vocab word. A critical value, or is it in the notes a critical number? I can't remember what he used.
Number/value.
Okay, so critical number / value. I think the book calls them critical numbers, and I was taught critical value way back when I was a little person like you, so I'll just go back and forth. They're the same thing. So critical value, critical number is any x value for which f prime of x equals 0 or is undefined. And all relative maxes and mins happen at a critical number. Absolute maxes and mins will happen either at a critical number or at a endpoint of an interval. Yes?
What was the point of showing us part B?
Part B
Yes.
of this?
Yeah.
Just to kind of highlight, the derivative doesn't have to be 0. It could be undefined. Usually it's 0 at a relative max or min, but occasionally it's undefined. That's the less common scenario. All right, so switch over to here before we get into the remaining examples. We have a few theorems throughout calculus that we have to know and be able to use. One of them from limits was intermediate value theorem. And intermediate value theorem, remember, said if you have a curve on a closed interval, so we have a definite beginning and a definite end, and the beginning and end are at different heights, and the curve connecting them is continuous, then for any height in between them, and an intermediate height, there's an x value where the curve takes on that height. So for a height, say right here, between the beginning and the end, there has to be an x value, call it c, somewhere in the interval where it happens. That was your intermediate value theorem. Here's our next theorem like that. It's called the extreme value theorem. Chapter 3 has a few of these. It's got extreme value theorem and mean value theorem and Rolle's theorem. which was named for a guy named Roll, who was lucky enough to live a few hundred years ago, so he got his name on a really simple theorem before anybody else got to come up with it themselves. So, the advantage of being dead, I guess. So, extreme value theorem. If your function is continuous and it's on a closed interval, then there's going to be an absolute max and an absolute min. So, here's like a picture of that. You have a closed interval from, call it A to B, and as long as the function between these is continuous, you're guaranteed to have an absolute max and an absolute min somewhere. So here, you just connect the dots from here to here, and no matter what you do, as long as your curve is continuous, you'll have an absolute max and an absolute min. And we can kind of fiddle with this and change it. So, all right, let's say here's our beginning and end. Let's erase these things. And no matter what I draw, as long as it's continuous, we'll have an absolute max and an absolute min. So tell me when I'm at the absolute minimum.
Yes.
Tell me when I'm at the absolute maximum. All right. So we had an absolute maximum and an absolute minimum. What if I draw it like this? Tell me when I'm at the absolute minimum. When I'm at the absolute maximum. All right. So absolute max and min could happen at the beginning or at the end, or at a critical number where the derivative is 0 or undefined. Stop it. Oh, I mean, that was a pretty good sneeze. Over here, we have examples of extreme value theorem does not apply. In this case, there's no absolute maximum or minimum because where it should happen, you don't really have a point because it's not a closed interval. And here, extreme value theorem doesn't work because your curve is not continuous. So, again, where you should have a maximum or minimum, you just have a holes with jump in the curve. Yes, ma'am.
That one makes like a horizontal line. The whole thing.
Yep.
Absolute maximum.
And the absolute minimum. So, yeah, if we just say, here is your curve, your curve is this really exciting flat line from here to here. That's not even flat. Let's try that again. That's marginally better. Every single point along the curve is an absolute max and also an absolute min, and that's allowed. And they decide that's the rule because we want the extreme value theorem to be true.
Are there any relative ones on there?
There would be no, I guess since everywhere the derivative is 0, also everything would be a relative max and minimum. So, but usually that doesn't happen because most of the things we look at are not flat lines. So that's your extreme value theorem. That takes us back into example land where we're going to see, okay, how do we go about finding absolute maximums and minimums? Today is only about absolute maximums and minimums. We're not going to worry about relative maxes and mins because they're a little more difficult. So absolute maxes and mins, if you're on a closed interval, find your critical numbers and then plug your critical numbers and your endpoints back into the function and see who's the highest and who's the lowest. And whoever's the highest is your absolute max, and whoever's your lowest is your absolute min. The x value is where it happens, and the y value is the max or the minimum. So I think that's in your notes at the bottom of your notes for 3.1 is your how to find extrema. So that's going to be what we're doing here. Questions before we do that? All right. So step A, find all the critical values of f of x. So you take your function f of x, and the critical values are when the derivative is either undefined or 0. So guess what you do to your function? Differentiate it. When in doubt, find a derivative. So you differentiate this thing. What's the derivative of 3x to the 4th minus 4x cubed? And then you see when is that equal to 0 or undefined. Now, in this scenario, can it ever be undefined? No. There's no fractions, nothing weird's going on. That derivative will never be undefined, but it could be 0. So let's set it equal to 0 and solve. How are we going to solve this? Factor out, what can we pull out here? 12x squared, who's left behind? X minus 1. So what are your critical numbers for x? X equals 0, and 1. So these are your critical numbers. So that's part A. Questions, Prince?
Why is the y coordinate? Why is it not relevant?
The y-coordinate is not relevant right now because the y-coordinate isn't really going to tell us where the maximum happens, but the y-coordinate is the maximum when we find it. So this tells us where to go horizontally to find our maximum or minimum, and then we plug these back into the function and compare the y's to see who's got the biggest y. So what we're now going to do is we're going to check f of x. And we got to check endpoints because we're on a closed interval, and we got to check our critical numbers. So what we're going to do is, I would just work through from left to right. So the leftmost point on the interval is at -1. And then I have a critical number at 0. And then I have a critical number at 1. And then my furthest right point is 2. So it just so happens that on this particular interval, it's all your whole numbers that we need to check. So you check these back into the original function because we want to see who's got the biggest y. So we're now comparing all the y's for these special values that we need to see. So you go back into the function, you see what happens when I plug in -1. You plug in, and you see what you get. And then you do it again for 0. You plug in 0 and see what you get for y, and so on. And then it's just, all right, compare. So when we plug in -1, what's -1 to the 4th? Times 3. What's -1 cubed? Times -4. 3 plus 4 is 7. You plug in 0. What do you get? You plug in +1. What do you get? What is it? Thank you. Okay, -1. And you plug in 2. That requires some thought again. What's 2 to the 4th? 16 times 3. What's 2 cubed? 8 times 4.
32.
48 minus 32 is 16. So that's just finding all your y values at these key points, the endpoints and the critical numbers. Who's our absolute maximum? 2. So this is your absolute max. So we'd say the maximum itself is 16 because that's the y-coordinate, that's the highest y value. And what's the minimum? At 1, right? Because that's the lowest y value. -1 is usually smaller than 0. So absolute minimum. So we'd say the minimum equals -1. So that's finding absolute maxes and mins on a closed interval. If you want to do it on just like the whole curve from -infinity to +infinity, at that point you're really just finding the critical numbers, plugging those in, and then you got to be careful. Well, where does the curve go way off to the right and way off to the left? Does it go off to infinity or -infinity? And for that, you need a fuller picture. But as long as we're on a closed interval, it's not so bad. Maybe it's a little tedious. Just to overview, you get your derivative, you set it equal to 0. You also find out where the derivative is undefined, if that is relevant. And that gives you your critical numbers. And then you plug your critical numbers and your endpoints into the function and see who's got the biggest and smallest y's. Follow up with that? All right, example 3. That clock is rolling on. Hey, thank you. All right, probably the last one for today. Your homework for tonight, originally I had this as like 2 different assignments. I cut some problems out and mushed them together so it's only 1 assignment for chapter 3.1, because after this, there's really not a whole lot else I can do with you guys on 3.1. So there's 2 answer keys in the folder for you to look at. Some of the problems are on one answer key and some of the problems are on the other answer key. So sorry for that. If you look at the problem set, it's like, that looks like a lot of problems. The last several are either true, false, or here's a graph Where's the maximum? Or is there a minimum? Yes or no? So it's not as many as it looks like. There's a few kind of like this. There's a few where you just get the critical numbers and stop. And then the last several, like 6 problems, are true, false, or here's a graph. Is there a max? So I don't think it's as much as you might think just based on the number of problems that are assigned. And that's due on Monday. Monday we'll move on to 3.2. All right. So find the critical values of f of x. So what do we do first? To find the critical numbers, what do I first need to find? The derivative. So go ahead and get your derivative. And what's the derivative? 2 minus 2. Very nice. Can you clean this up and make it look a little nicer? Factor out 2. Suppose we could do that. What else could we do? Subtract the 2's. Okay, so you could set it equal to 0. Yeah, so let's just do that. So set it equal to 0. I was thinking throw x down the stairs because he has a negative exponent, but whatever. We don't need to do that. So set it equal to 0. So you said subtract the 2 over. And then they cancel out. So we end up with x to the negative 1/3 equals 1. If x to the negative 1/3 equals 1, then what does x have to equal? Still 1. Because to kill that, you need to raise it to some power. You don't even need to worry about what power it is. You're raising it to some power to kill an exponent. 1 to any power is still 1. So that's one critical number. That's for when f prime of x is 0. Is there an x value that makes this undefined? And that's where having this written without the negative exponent is maybe helpful. So if you think f prime of x is also 2 minus 2 over cube root of x, what x makes that undefined? Right, so you say that's undefined for x equals 0. So these are your critical numbers. So if you end up with like a negative exponent, you're going to have a value probably that makes your derivative undefined, because that negative exponent is really saying, there's a fraction, throw me down the stairs. And then you'll have probably both a critical number where the derivative is 0, undefined, and a critical number where the derivative is 0. And then, once you got those, you can do your check of all your special numbers. So you take your endpoints and your critical numbers, and you check f of x. At endpoints and critical numbers. So you're going to have to check f of negative 1, f of 0, f of 1, and f of 3, and compare them all. And just remember for that, you're going back to the original function f, because y equals f of x. So I think you guys at that point can do that for yourself. That's just a matter of plugging a bunch of numbers into your function and seeing what you get, right? Do you guys have any comments to follow up on this? Or any questions or clarifications you want me to make? Okay. Does anybody happen to have these done? 0, 0. Okay, that's cool. That's negative 1. That's probably negative 2. I'm guessing this is negative 5, but I'm not like 100% confident. And this is going to be some decimal. So
I got 1.
What? Because 2 is not an endpoint, and it's not a critical number. So we only need to check these values that are either endpoints or critical numbers. So You got your homework for the weekend. Also, make sure you do your delta maths. Also, one of the delta maths is related rates. And Lucas told me that if you do things in terms of decimals, you have to take it out to like 37 decimal places or it doesn't accept the answer. So I will grade this week's out of 6 instead of 8. If you don't do the related rates one, no harm done. If you do the related rates one, you get extra credit. So you can get up to an 8 out of 6 on this week's delta maths.
I did the related rates, and now he said you didn't need to do it. I'm so bad. I've been done for like